So we have already finished the introduction and the fundamental mathematics of the robots modeling, which is the homogeneous transformation matrix. And last week we have finished the forward kinematics. And today we will be doing the inverse kinematics. So just for recap, so what is the forward kinematics? So the forward kinematics is transferring the joint variables to the poles of the any factor. And the method for computing the forward kinematics can be through geometric or through the homogeneous transformation matrix. So which is, we have taught last week, is the DH method. So this is the DH conventions, the rules. So when you set up the local frames, you need to follow these 4 rules, or 3, basically 3. And the 4th one is the x must intersect with the z-axis before it. And these are the 4 DH parameters. So through these 4 parameters, we can get the transformation matrix very easily. And this is the general form of the DH transformation matrix. So zero robots, which is we have a base frame, and this one is the any factor frames. So in between, these are all the joints, like such as revolute joints and prismatic joints. And when we want to transfer all these joint variables to the any factor position and the direction, so it's the any factor pose. So how to transfer the joint variable to the any factors configuration is through the forward kinematics. So this is the same figure or same slides as the last week. So last week we have taught from the joint variable, which is you can say theta or d. So combination we can call it q. So forward kinematics is transferring the joint variables to the any factor position, and reverse will be the inverse kinematics. So the inverse kinematics is transferring the any factor configuration back to the joint variable. So what is it? What is the inverse kinematics used for? Can anyone give an example? What is the application for the inverse kinematics? So for example, we have a robot, and this is the base frame. And a robot, and here. So we know this coordinate in the base frame is 0, 0, 0, right? And if we want to grab objects, and these objects, the position may be, we're given like 10 and 5 and 17, for example. So we have 3, here we have 3 joints. So what is the value of these 3 joints? So we can get this any factor to the point of the object. So from 10, 5, 17, and transfer back to theta 1 equals to theta 2 and theta 3. So So this is inverse kinematics. So if we have already have an aiming position or aiming configurations, we want our robot to move to the configuration we want. And this is through the inverse kinematics. And basically, these are all the trigonometry. And you may be using this trigonometry in solving the inverse kinematics. So in our controllers, so normally a robot kinematic control, we have an aiming orientation and position. Through the inverse kinematics, we transfer these to the orientation and position to the joint variable, such as the theta for the variable joint and the d for prismatic joint. So after we know each joint need to like moving or how many degrees or how many centimeters or millimeters, then we can do the actuations. Then we check, this is a closed loop, and we check whether the robot has get to the position. So this is how the inverse kinematics works in the robot's application. And there's a workspace. If any robot has a workspace, so this is the bridgeable workspace, or you can call it primary. So it's a set of all position P that can be reached with at least one orientation data. So if it's a reachable configuration, it's a primary workspace. And the secondary workspace will be a dexterous, which means that this point, this position that can be reached by any orientation. So for example, this point for my arm, I only can reach it in this orientation, like the first point. I cannot change, I cannot have any other orientation. But if a point here, I can reach it in different orientation, any orientation. So this will be considered a dexterous workspace here. But the first, I can only reach it in this configuration, but not others. So the primary is can be reached with at least one orientation, so which is the furthest or the largest workspace, and the secondary will be a dexterous, which can be reached by any orientation. So we know that the secondary workspace must be included in the primary workspace, because the primary will be the largest workspace. And next, we'll be introducing the inverse schematic solutions. So you can see the configuration of the position of this end effector is here, and the direction is aiming in this direction. And for this robot, it has 4 different solutions, which means that with 4 different theta values, different sets of theta values, it can, all the end effector has the same configuration. So why will it happen? Why we have different solutions? Or you can say multiple solutions. So if we have 2 links, if we want to reach this point, how many possible solutions will there? If we have 2 links. So it should be 2, right? Another solution is the opposite. You can flip it and he can still reach this point with the same leaf length, but different angles. And if you imagine that we have a robot in the first joint, which is V0, and this is the end effector. We want to reach this point. One solution, it may have like in this point, in this direction, and another one within this, you can turn a pi degree, so 180 degrees, and we have the another solution. So you can see from this one to this, the first joint turns 180 degrees. So this is called the left, and this is called the right. So it is the same as our shoulder, that we can have our right arm or our left arm reaching, and another one is if we thinking we rotate our arm 180 degrees, then we have another, like here we can also reach the same configurations. And also through the elbow down, so this is the elbow, so this one is the elbow down, and here is the elbow arm. So the left means the arm, here is left, and right is in front is right, and the elbow down means that it's in the below the joint and the end effector, this line. So this is called elbow down. So and above means that above this joint, these two joints, the line connected these two joints is above. So if we see there's a so above this line means elbow up, and if it below, it's mean elbow down. So through this, we have 4 different solutions. Just we have 3 joints. We have 4 different solutions. So this is right up and right down. So this is, if the arm is in front, it means right, and this is up and down. And the arm is behind, so it's left, and this is up and down. So we want, through the same configurations of the end effector, we can have 4 different solutions for inverse kinematics. So this is a typical 6 degree of freedom industrial robot. So normally 6 degree of freedom robot arms is have around 8 different solutions. But when you have all the solutions, you need to check it. And some special types, such as we'll introduce later. So a special 6 arm means revolution joints, or you can say 6 degree of freedom robot arms. You will have the max solution is 16. So we'll show the kind of the robots that which have the 16 solutions. So through the analysis-based algebraic transformation of the robot kinematics, we can solve multiple solutions. So this is an example of an orthogonal robot, which means that all the joints were connected in 90 degrees, so it's orthogonal. And this kind of robots will have 16 different solutions. So the first page, you can see there's 8 solutions, and the second page, there's another 8 solutions. So in total, there will be 16 solutions to reach the same position of the n effector. So you can see all the n effectors has the same position here, reaching the same position. All the n effector has the same position. And it has 16 different solutions. And if there are robots that has more than 7 joints, because we know our environment or our space is 60 degree of freedoms, right? So normally a degree of freedom joints can contribute to 1 degree of freedoms each. So if there are more than 6 joints, then this kind of robots will have more than 6 degree of freedoms. So it's called the redundant robot. So the n is a joint number, and the m is the position and orientation of the n factor. So normally, if a spatial robot is 6, and a planar robot will be 3. So if n is greater than m, and we call this kind of robots is a redundant robot. And the redundancy is n minus m. And this only applies for the serial manipulator. So this is a 7 joint robots, or you can say the degree of freedom robots. And it's a Kukas LBR EWA 7. And when you solve in the inverse kinematics for this robot model, you will generate infinite solutions. So like we have an n factor at this point, you can imagine that this robot arms can rotate above this axis, so it will generate infinite solutions. All the solutions, when you rotate, you will get into this position. So in general, there will be 2 kinds of methods to solve the inverse kinematics. The first one is the analytical solutions, and which we'll be doing the analytical solution today. So it's preferred if it can be found. That means that this kind of solution is difficult to find. And it's usually you can use the geometric inspection to assist your solution, to solve your solutions. And also, usually we're using the algebraic method. So just solving the polynomials. And this is a systematic way for generating a reduced set of equations to be solved. So if you can get the analytical solutions, it's preferred. So if you want multiple solutions, you want to get all the solutions of the inverse kinematics, you need to use the analytical solutions. And on the other hand, we have the numerical solutions. So because if we have redundant robots, that means that we will have infinite solutions for the inverse kinematics. So in this case, we need to use the numerical solutions. And it's slower because for the numerical, you need to try out the numbers. And a way is using the Jacobian matrix of the forward kinematics. So we'll be teaching the Jacobian next week. And there are some like Newton method or gradient method. So it is just try and errors to find the correct number. So for the analytical inverse kinematics, the inverse kinematics problem consists of the determination of the joint variables corresponding to a given n factor position and orientations, which means that in this kind of problems, we'll give you the position and the orientation of the n factor, and you need to find out the joint variables. So the analytical inverse kinematics equation can be derived from the fluid kinematics equations and using the trigonometric identities. So we'll teach you how to derive the inverse kinematics solutions. So if you recall from the last week, if we have a robot, a two-arm robot, the first joint is Q1, or you can call theta 1, and here is Q2. And the fluid kinematics of this robot can be written as for the x component will be A1 times cosine Q1 plus A2 times cosine Q1 plus Q2. And for the y component will be A1 times sine Q1 plus A2 times sine Q1 plus Q2. And for the theta is Q1 plus Q2. So this is the fluid kinematics we taught last week. So for the inverse kinematics, it means that we'll be given a set of x1, y1, and theta 1. And we want to find Q1 and Q2. So this is an inverse kinematic problem. So we call it IK. And sometimes we'll be given directions, or sometimes because for this, if we get direction, there will be only one solution. If we get only one position, then there will be two solutions. So for this example, we'll be given x1 and y1, and we want to find q1 and q2. So how can we derive q1 and q2? So if we see the equation here, this C1 means cosine Q1 plus Q2. And so C1 means cosine Q1. So we can square Px and Py, and we can get these two equations. And we can sum these two equations up. So we get on the right side, or this is right side, is Px squared plus Py squared. And on the left side, because cosine squared plus sine squared is 1. So it's A1 squared plus A2 squared and plus 2A1, A2 cosine 1, Q1 plus Q2, and plus 2A1, A2 sine Q1 times sine Q1 plus Q2. So on the right, we can write it as Px plus Px Py squared equal to A1 squared plus A2 squared and plus 2A1 A2 C1 C1 2 and plus 2A1 A2 sine 1 sine 1 2. And we can recall from the trigonometry. So cosine theta 1 times cosine theta 2. Here is plus sine theta 1 times sine theta 2 is cosine theta 1 minus cosine theta 2. So we apply this relationship to here. So we know that cosine theta 1 times cosine theta 2 plus sine theta 1 sine theta 2 is equal to cosine theta 1 plus sine theta 3. So we apply this one to here. So it's equal to a2 squared plus a1 squared plus this 2 times a1, a2, and times cosine minus q1, q2. So A1 is a linked length, A2 is also a linked length, and Px, Py we get from these are the given variables. So these two are given, and we know the linked length. So the only variable is the Q2. So through the law of cosine, then we can get the value of Q2. And usually we'll have the cosine and we transfer it to the sine and we use tangent, arctangent to get the Q2. So we know that the sine Q2 will have plus and minus. So there will be two solutions for the Q2. So in geometric form, if we see this is 0, and we have here, so here is Q2. So for this solution, is its Q2 positive or negative? For this solution, is this Q2 positive or negative? So here is 0, and we rotate a degree. So this Q2 is positive or negative. So it's positive solution. And for another solution, we can see here is Q2. Right. So this Q2 solution will be negative because here is 0. So if we rotate from this line in this direction, the Q2 is positive. And if we rotate from this line to this solution, this Q2 is negative. So these are the two solutions for the Q2. And then so after we already derived the Q2 values, we need to find the Q1. So we already have the Q2, and we want to find Q1. So back to our Px and Py equation here. Then we can, if you see this one, is cosine Q1 plus Q2. So we can apply this relation over here. So we can write cosine Q1 plus Q2 cosine Q1 plus Q2 will equal to cosine Q1 minus times cosine Q2 and minus sine Q1 and sine Q2. So we can get these two equations. And if we times cosine Q1 in both sides, then we can get this two. This is times cosine Q1 in both sides, and this will be times sine Q1 on both sides. Then we will get this. And we sum it up. We know that this all cancel off. So we get A1 cosine 1 squared plus A1 sine 1 squared, which is the A1. And here we can see is A2 cosine Q3. So we can get this solution. And if we minus, then we can get A2 sine Q2. So we derive these two equations over here. And then we can just square and sum it up. And we can get px squared plus py squared times c1. And here we get px times a1 plus a2 and z2. So from here we can get cosine q1, and from here we can get sine q1. So if we have cosine q1 and sine q1, that means that through a arctangent equation, then we can get the value of q1. So beware that there will be a q2 in your equations. So we need to substitute our q2 derived from earlier into these two equations. And there will be two equations, means that there's a positive q2 and a negative q2. So there will be two q1 solutions. So the q1, the first solution is over here, and q1, the second solution is over here. So the inverse kinematics for the two robots, the q1 is equal to this one, and the q2 it will be equal to this equations. So is this okay? It's just derived from, you just find the relationship between the equations and try to eliminate all the unknown variables and only left one variable, so we can find the value of the variables. So this is maybe it's the simplest inverse kinematics for the robots because it only have 2 arms. So normally for our industrial robots we have 6 arms. So the inverse kinematic may be much more complex. And now we come to 3 arms robots. It is we just like implement a tool after a joint and tool after the 2-arm robots, become 3-arm robots. So how to find the inverse kinematics for this kind of 3-arm, 3 revolutionary joints arm robots? So we are given all the link lengths. So the link length for the first link, second link, and third link. And also the P, we have Px and Py, and theta means the direction of the any vector. And we want to find Q1, Q2, and Q3. So the first thing is that if we have a link, such as this one, and we know its direction, so it's theta. And this point is P, X, E, Y. And if the link length, this one is A3, so what is this point, the position of this one? We know that the length over here is A3 times cosine theta. And height is A3 times sine theta. So this point will be Px minus A3 times cosine theta for the x, and for the y is Py minus A3 times sine theta. So we can get the position of this point. So if we see in this robot, this is the aim vector. We have Px and Py, and the direction is theta. The angle is theta over here. So if we want to find the points of the W, we can get through this relationship. And this is for the right side. And for the left side, we also know that these two are the two R arms, which we have already solved, right? So we know that for this point, PWX, PWY is equal to Px minus A3 times cosine theta. PWY is equal to Py minus A3 times sine theta. And it's also it's equals to the 2R aim vector points. So it's the same as these two equations. So we can put it together. So we can get Px minus A3 cosine theta equals to A1 times cosine 1 plus A2 times cosine Q1 plus Q2. And for the y, the same. So in the same process, if you already solve into this, it's all the same as the 2R because you just see Px, Py, and you can use the method you already learned in front. It's equal to this solution. And so it's same, so we squaring and sum the two equations, and we can find the cosine Q2. And through the arctangent, then we can get the value of the Q2. And it will have two solutions, the plus and minus. And so we can also see what will be happening for the solutions. So if we have two robots, if it is in a straight lines, how many solutions will be here? Will it be here? How many solutions? How many possible solutions? If we want to reach this point by a 2R long, it will be only one, right? Because only all straight. But inside, any point inside, then we can find two solutions. And so if the arm is in a line, so if we want to go to this point, so you need to bend it back. So we will only have one solution. So we can determine by the roots. So if there are two real roots, it means that it's smaller than 1. And if there are only one double root, it means that it's all in the straight lines. So it's in the maximum reachable workspace. So if there will be no real roots, what will be a no real root? So just now we have already explained secondary workspace and a primary workspace, and there's a workspace outside the primary, right? So in the primary workspace, here will be k smaller than 1, and for the reachable will be equal to 1, and here will be above larger than 1. So here, because the robot cannot reach, so we won't have any solutions. And here we only have one solution because it's the primary workspace. And here, for the dextral workspace, we will have two solutions. So for equal to 1, the arm is in the full stretch or folded configurations. So that you will only have one solution. And if it's larger than 1, the position is not reachable. It means it's outside the reachable workspace. It's something like over here, so the robot cannot even reach. So if we've given a point over here, you cannot find any solutions. So if you've given a point on in the straight line, this is the largest, the furthest point, position you can get. So here, in this point, we will only have one solution. And in between, you will have multiple solutions. So for this example, you have two solutions. So back to the inverse schematics. So we can have our sine Q1 equal to here, cosine Q1 equal to this. So this is same as the two-arm robot. And through the arctangent, we can get the Q1. And we know that the theta is Q1 plus Q2 plus Q3. So if we have theta minus Q1 minus Q2, and we can get Q2. So this is about kinematics. So if we have like here a robot with 3 arms, so we have the first one is link 1, link 2, and link 3, and this is the n effector position, and this is the trajectory. So if we move in the joint value, then we can see that this robot will be folding. So this is through the forward kinematics. So we're transferring the theta value to the n effector, px and py. And backwards will be given the tool position px to py, and through inverse kinematics, then we can find the joint values. So until here, is this okay? Or is it too complex? It's just solving the basic the polynomial equations. So we only have 5 minutes left. So maybe we'll start doing the scoreboards after the break. So maybe we can take a break now. So if you have any questions, you can come and ask me, or you can just practice to solve the inverse kinematics for like for 3 or 2 hours.
You don't have a midterm exam, right?
We have.
You have?
Yeah.
When was it? Because I couldn't see it on the schedule.
Yes, it's on the schedule. Let me check. So the exam is on November 25th. So we only have one exam and one presentation.
Because it's not the midterms, we just have about 2 or 3.
Yeah. Because we're gonna have one, so it's in between the midterm and final.
Yeah. And will it be similar to the homework?
Easier than homework.
Easier. Okay.
Yeah. So it's basically all on the slides. So if you can derive all the equations or all the models on the slides, then we can do it fine. So the slides we only taught the planar and up to the Scala or this one will be 5 degree of freedom robots. For the homework, you will be deriving the 6 degree of freedom robots, which is the general industrial robots. But for the midterm, I think the maximum will be 4. Yeah, so it will be much easier than the homework or the slides, because you cannot use like something like MATLAB to like do the equations. So it will be easy.
You can use MATLAB.
You cannot use the MATLAB. So it will be easy. Yeah. So maybe we'll take a break, and after that we'll come back to the scoreboards. And we want to find the inverse kinematics. So for last week, I think also you have known how to derive the transformation matrix from the base frame to the any factor frames. So if we times all the transformation together, then we can have a transformation from the base frame to the any factor frame, which is a 4 times 4 transformation matrix, something like this one. And we name the elements inside this transformation matrix as U, V, W, and Q. So for the U, V, W will be the rotation matrix, and for the Q will be the position vector. So I hope you already get familiar with the transformation matrix. So the first thing we want to do is we multiply the both sides by the inverse of 0 to 1. So the inverse kinematics, we need to derive the forward kinematic first, and we get the equation, then we can do the inverse kinematics. So this is the forward kinematics, and we want to times the inverse of the first one. So these two will be eliminated. So we get this one, A to 1 to 5. And we get the first column. Since we don't have the forward kinematics here, but we'll explain it later. So for UX, UY, and UZ, then we can get UX times C cosine Q1 . So we know that A05 is UX, UY, and UZ. And we times the inverse, and we can get the first column here. The UX, U1x is equal to US times cosine cosine Q1 and plus Uy times sine. So this will be equal to, I think all this should be done in the MATLAB so you can have all these kind of equations. And we can find these three kinds of equations. So UZ minus UZ is equal to sine Q theta 2 plus theta 3 plus theta 4 and cosine theta 5. So here we have a minus UX cosine Q1 plus Uy times. I think here we have missed out. Let me check it. Maybe I think it's cosine. So through the fourth column, if you have the four kinematic solutions, then you can find the three equations. So from the equation number 8, it's a fourth column is minus Qx sine Q1 plus Qy times cosine Q1 equal to 0. So we bring it over here, so we can find that for the arctangent Qy minus by Qx, we can get the angle value of the first joint. So for the first one, we will have two solutions. So it's the Q1, and if it's another solution will be plus 180 degrees. So it's in the reverse side. So you can recall that for the first one, if the robot falls in this plane, then one solution will be here, and the one solution will be reversing 180 degrees. And once Qy is found, the two solutions for Q5 can be obtained from the equations. So if we found equation 5, so for inverse kinetics, it's basically just altering with the equations and finding to eliminate all the unknowns and left only one unknown, so you can solve the value. So if you see these equations, once we already know the value of Q1, then we can solve the Q5. So I add the cosine over here. So we can solve the value of the joint 5 by using these equations. So remember that Q1 has two solutions. So Q5 will have two solutions also. And corresponding to the each joint, here is 2, 3, 4. So we can find the theta 2 plus theta 3 plus theta 4 using the Q5 and Q1. And then through these equations, then this is the theta 2 and theta 3. So we square it, then we can get Q3. So the equation of the theta 3 is this one. And then once you get theta 3, so we can get theta 2, because 2 and 3 are linked together. And the last one will be Q4. So we found the Q2 and 3, and we just use just now we have already find the theta 2 plus theta 3 plus theta 4 and minus theta 3 and theta 2, then we can data flow. So in total, we'll have 8 inverse kinematic solutions. And afterwards, we'll try to derive the inverse kinematics with you. So this is why there's 2 solutions for Q1. So if you see that a robot is rotating, you can see that this kind of robot is moving in the plane, within this plane. So if you find a position over here, so this is the origin positions. So we can set up a plane over here. So the robot is moving within this plane. So the theta 1 must rotate, that the robot rotates into this plane. And within this plane, we'll have 2 solutions. So one will be some like this one, aiming in front. If you rotate 180 degrees back to this point, and it's also within the plane. So for theta 1, we'll have 2 solutions. And this 2 solutions is, the difference between these solutions is 180 degrees. And another technique for solving the inverse kinematic is that once your orientation of the n effector has known, so you can minus the link length of the last links, the 2 links, and you can find the joint position here. So these are 2 techniques we usually use when solving the analytical inverse kinematics. So this is an example for a 6 degree of freedom, so which is for your homework. So this one is T. So we know that for last week for your homework, you will have 6 joints. And together we can get the 4 kinematics for a 6 degree of freedom robot. And now we times the inverse of the first transformation matrix over here, then we can get so for the first one, the inverse will be cosine theta 1 and 0, sine theta 1 and sine theta 1 and 0. 1, 0, minus A1, 0. So this will be the inverse of the first transformation matrix. And you times the results of your 4 kinematics together. So then you get these 2 equations are the same, so which means this one times this one. And from inside, you need to find, like, we know this position, right? And we found that Px and Py we know, we also know. So here we only have 1 variables. You can see it's Q1 and C1, so we can easily get the Q1 from this relationship. And another technique is, we know that 6 degree of freedom robots, we can separate into the arm and the wrist. So the arm is the first 3 joints, and the wrist is the last 3 joints. So which means that we want to times the first 3 joints, the inverse in front, so we will have This one will be the risk. And so on the left-hand side, the 12 elements are equal to here. On the right-hand side, T4 times T5 times T6, the 12 elements are equal to here. So we just finding the relationship and try to eliminate the unknowns. So this is how you solve in the inverse schematics for spatial robotics. So this will be your homework. So if you check on Moodle, so your homework is basically solving the inverse schematics for the robots you have done for the last week. So in the same robots, the follow-up robots. So for this week, your homework will be solving the inverse schematics. And for problem 2, is you just given a joint angles, a set of joint angles, and you use this set of joint angles and into your forward kinematic solutions, and you can get your n factor configuration. And you use this n factor configuration and through your last question solution, the inverse kinematics, then you can get your a set of joints or maybe multiple sets of joints solutions, and you need to verify whether inside there's a set of your solution is same as your input. So this will be your homework for this week. And because the inverse solution kinematics may be complex for the 6 degree of freedom robots, so this one we'll have around a month to do. You'll have around, so 4 weeks. You can do this homework for 4 weeks. So I think this will be the hardest problems you'll be solving in this course. If you can solve the 6 degree of freedom robots inverse kinematics, I think the robot modeling will be fine. So this is the same robots. So first we will derive the forward. So the forward is, this one will be your homework for last week. So from the first joint to second joint and to the 6th joint, joint number 6, and you times it together, you can get the forward kinematics. There will be 12 elements over here. So these are the forward kinematics, and you can verify it through the MATLAB. So you just plug into a set of joints, then you can get the transformation matrix. And for inverse, you need to solve it. So these are the hints for the equations you have, and you try to solve it each one joint by another joint. So the first one you can find as θ1, and this is, you find it the equation 8, and you can get θ1, and then you find θ3, and then you find theta 2 or theta 3, and you can get it, and you find theta 2. After that, then you can find theta 5, theta 4, and the last one will be the theta 6. And you will just input all your formulas into the MATLAB, and you can derive the 8 sets of inverse kinematic solutions. And you can verify it if you input a set of joints, and this is the transformation matrix generated by a forward kinematic. And this is the robot configuration. And you input the forward the configuration, the transformation matrix over here, and you can generate the 8 sets of inverse kinematic solutions. Then you can compare whether the input before is a solution over here. So I think this will be all your homework. So just derive the inverse kinematics, and then give an example and test it whether you can find the input through the forwards and inverse. Then you can get the same solution. So any question for the homework? It's okay? So we have a practical assessment today, and Ben will be introduced the product practice.
So, hi everyone, my name is Ben. Before we start, does anyone want to go to the bathroom or take a break or something? We can, if anyone wants to do that, then we can start that. No? Okay. So, my name is Ben. I'm a master student from IMR, from Professor Lin's lab. And today we are going to do some practice about inverse kinematic and the forward kinematic. So first, we want to solve inverse kinematic of a 3 degree of freedom robot arm right here. This is the target you want to solve today. So later today, we will build a model of it, and then we will try the inverse kinematic solution on it to see if it's the same of your simulation. So second, we will use MATLAB to do that, and we will visualize a robot arm skeleton. And I will teach you how to do that with MATLAB. And the third, we will use the soft answer to control the robot arm to validate our solution, just like I said. And so today we will do something about determine the correct DH table from by dimension. Later I will give you the dimension of the robot, and then second you will derive the inverse kinematic and found Professor told you guys today, right? A robot will have floor solution, right? So you just only need to find one, and third, you will visualize the full kinematic skeleton, and then try it on this one. This practical is implemented by group. So if you are not sitting with your group members, you can move right now. Okay, so yeah, first we can see this robot arm. So this robot arm have three joints. The first joint is this. It can rotate about this axis. And here's the dimension. You can find the worksheet of today's practical on Moodle right now. So you can download the materials right now. And then, so the second axis is right above the first axis, and a little bit offset to the right, to my left, and with 11.23 millimeters. And then the third joint is the same orientation with the second ones, and its distance is 150. And then the end effector is another 100 millimeters. So for you to understand, you can see the rotation is like this. So remember this, and this is gonna impact how you build a model. You need to first draw the kinematic diagram, right? You need to know the axis orientation. Okay, so remember this. Second, we will use MATLAB script to help us to derive and visualize. So it's actually opposite. We want to do the inverse kinematic first. After I give you a position, I want your team to find. And first, you want to build the DH table of this robot, and then you input the position I gave you, and then you derive it. After you derive it, your script should output the theta. With the theta you obtain, you can input into your full kinematic. Also, the full kinematic still needs a DH table, and then you input your theta, and then use standard DH transformation metrics. I believe you can find it in your slides last week. And then you can plot and then connect the joints to form a skeleton, just like this. All right. Before we start our explanation on the script, I want to talk more about this is not gonna be in our scale today, but still, you can, after today's lesson, today's practical, when you go back, you can try the workspace. If you have a range of your actuators, then you can use it to build, to visualize the workspace like this. My method is using a point cloud, which is in theta 1, I build a space from negative pi to pi 2, and then I give it 30 points, so which will be 12 degrees, no, 12 degrees per dot. So it will start to get all this dot, and then one by one, you can have a points group as a cloud, just like that. So that you will know how's your accessibility. And then second, today we are going to find only one solution, but if you want to find all of the solutions, you can use this kind of trick. You just So in our situation right here, in our case, only the first theta will change the orientation on the xy plane, right? So you only have two theta. One is the positive one, and then one is plus pi, plus 180 degrees. You will have a backward solution, right? So it's an easy one. So if you can find theta one, then you can use this theta one to find another solutions. So it will be like a nest, two-layer nest. So this is a easy version that if you want, I will give the workspace and the whole solution script after this class, because I've already solved the inverse kinematic in those scripts. So I want you to manage to do that by yourself at least one time. So after this class, I will upload it. So okay, so let's see the inverse kinematic script first. Okay, you might want to take a full shot or take a photo or something, or take a screenshot, because I didn't give you this, so try to solve it at this once, okay? So first, you want to input your target and the effector position. So right here is 100, 100, 100. So we want the end effector to be 100, 100, 100. And we already have the DH table of this robot. And then we solve theta 1 first, because just like I said, only the theta 1 will impact the position on XY plane. So it's an easy one. After solve the theta 1, you can find the projection of the YZ, XZ, and then find a new plane. And then I will save the rest to you guys. You can find it. It's an easy one. Only 3 degree of freedom. So after all this, I just list the theta 1, theta 2, theta 3, and bring it out. So the whole thing will be like this. The whole output will be like this. 3 theta. And it's in gradient. So this whole script, you will need to solve it yourself. Alright, let's see the forward kinematics. The forward kinematics, I use the dash method. And dash method, so first we have to know the dash table. So try to sketch your kinematic diagram. And then after you sketch your diagram, you should know your dash table. And then put in your theta. The theta right here is actually this. So we will know the posture I need to get to the designated point position. And then I gave it this right here is initialized. So T is a 4x4 matrix, and then the points is a 3 times. If we are right here, our joint number is 3, and its joint number plus 1 is 4, so 3 times 4 matrix. And then this is all initialized. Inside of this matrix right here, right now, is all 0. It's all 0 volume. And then we use a for loop to derive our DH. So this one, remember this one? This one is a standard DH. So also you can find it in your last week's slides. And by every iteration, the T will minus this transformation matrix 1 times. So can anybody tell me how many this loop will go? How many iterations will go in our case? how many times you will iterate? From 1 to join number, which is 3. So you will iterate 3 times. Okay? So after you iterate 3 times, every time you will record the joint point, the joint position. So after we know every joint position, we can just connect it using the plot3 function. The plot3 function is just connect 3 points. Alright? So put in your points one by one, and then it will become a skeleton. Just like this. So this is one of the solution of 100, 100, 100. Alright? So this is what you do. First, you need to solve the inverse kinematic, and then found the forward kinematic. And then draw this skeleton. After you draw this skeleton, then you can come to me and then try it on the real robot and make some record. Go back and then finish your worksheet. Discuss with this result. Okay? Understand? Any questions? Is this clear enough? If you want to ask in Chinese, it's okay. Any questions? Alright, then the materials is all in Moodle, so go download your materials. And these two, this DH and IK3R is already in your materials, so use it. I already did the part I want you to do, so go ahead and try it. If you have any question, just raise your hand, and then we can help you. All right? Discuss with your teammate. Okay? That's it.
So for the practical worksheets,